Here's an elevator. So the elevator, my little cable, let's put it on top so now we're going to stand there. Let's have me get on this elevator. So I have a mass of 70 kilograms, but because I'm a little bit odd, I bring with me a scale. Now the scale I'm going to stand on, and here's a little scale reading. All right. As I look down at my scale reading, let's do this. Let's take a little free body diagram of me. Gravity is pulling me down. Something is pushing me up. That is the scale. The scale is pushing me up, but it's pushing me normal to its surface. It's perpendicular to the surface, so this is going to be the normal force. So as I stand here, the sum of the forces that are on me are the normal force, which points up, and then the force of gravity, which pulls down. And this has to be mass times acceleration. But in this case, in situation where I just walked in and stepped on the scale, I'm not accelerating up or down. So my acceleration is 0. What does my scale read? Well, the sum of my forces, A equals 0. So the normal force minus the force of gravity equals m times 0. So the normal force has to equal the force of gravity, which is nice because that is the scale reading. Oh, look, it reads my scale. It reads my weight. So now let's accelerate upward at 5 meters per second squared. I press the 15th floor, and we'll find what's up there. I think there's dishwashers. So the normal force, sum of the forces have to equal ma. The normal force minus the force of gravity has to equal my mass, which is 70 kilograms, times the acceleration, which in this case is 5 meters per second. So what does the scale read? Well, normal force has got to read, this has got to equal 70 kilograms. 7 times 5 is, I'll multiply it out in a second, plus the force of gravity, which is mass times gravity. So I have 350 plus my mass, which is 70 times 10, 700. 700, that's why I do it by 10. So I end up with 1050 newtons. So now it reads more than what it did when I was resting alone, which I didn't do, but then it's mg, which is 700 newtons. It's going to read harder. Well, it kind of makes sense because that scale is doing two things now. It's both supporting my weight and pushing me up. Now what happens when I decide, oh no, I have to get out of this building. I got a call. Something important happened. Well, let's step off here for a second. And let's go down. Now let's just have my scale here, and I'll stand on it. All right, so gravity is pulling me down. The normal force of the scale is pushing me up. So the sum of my forces have to equal ma, and the sum of my forces are the normal force minus the force of gravity, and that's got to equal ma. So I decide to fall. So now my acceleration is negative 5 meters per second squared. That usually happens right away. Feels kind of, goofy. So the normal force, which is the scale reading, is going to be equal to ma, which is negative 5 plus the force of gravity. So what's the scale reading? 70 times negative 5 plus 70 times 10, negative 350 plus 700, and that equals 350. Yay, I did that right. Oops, positive 350. It's reading less. Well, because the scale doesn't have to push up on me as hard because it's letting me fall. Right? It wants this to stay down, right? But it doesn't have to let it go very far. So let's say somebody does something nasty and breaks the cable and lets me fall. So now I'm falling at 10 meters per second squared in the negative direction. Sum of my forces equals ma. I have normal force in the positive direction minus force of gravity, and that has to equal mass times acceleration. In this case, it's negative 10. So normal force is going to equal to mass, which is 70 times my acceleration, which is negative 10, plus the force of gravity, which is 70 times g, which is 10. Oh, look, the normal force is 0. The scale is going to read 0 newtons. I am weightless. Oh, look, that's off the screen. I am weightless. There we go. But really, that's not what's happening, because I still have some weight. The force of gravity still exists on me. I just don't have a normal force. So a better way to say weightless is really normal forcelessness. Yeah, that's really going to catch on.